So what is GCD? So its full form is Greatest Common Divisor. Okay, so to understand this definition, we first understand what is division. So let's first go through even basic definitions, and let's go through some very basic definitions. So what are like integers? So integers are like numbers minus 1, minus, let's say minus 2, minus 1, 0, 1, 2. Let's get it's hanging a bit, and so on and so forth. So from minus infinity to plus infinity. So these are like integers, and real numbers are maybe like 1.5, maybe like minus infinity, minus 1.5, minus 0.5, 0, 0.5, and so on and so forth. And so maybe like these two definitions will work for 0, 1.0, 2.5, 5, 5, 5, 5, 5, 4 by 3, dot, 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 till infinity. So for like today's lecture, we will focus only on integers. We will so the definitions that we have, most of them may apply for real numbers as well, but we will mostly focus on integers today. So GCD is, so let's define what is a divisor first. So a divisor of a number is some number. So divisor of a number n is some number x, that some number x that divides n perfectly. So for example, does the number 3 divide 9? Answer is yes. So 3 is a divisor of. So does number 5 divide 9? Perfectly. Which is remainder should be 0. But in this case, what is the remainder? Remainder is 9 by 4. 4 into 2 is 8. And remainder is 1. So is 4 a divisor of 9? Answer is no. 4 is not a divisor. Fine. So let's write down all divisors of 9. So is number 1 divisor? Yes. Is number 2 divisor? No. Number 3 divisor? Yes. Is 4 divisor? No. 5 divisor? No. 6 divisor? No. 7? No. 8? No. 9? No. 9, yes. So what are the divisors? So these are 1, 3, and 9. So if you want few more example, so let's write down divisors of maybe 10. You can see it will be 1, 2, 5, and 10. These are the divisors of 10. So greatest common divisors of some number, GCD, of some numbers is the largest number that is the divisor of. So let's first define GCD of two numbers. Let's say GCD of two numbers a comma b is the largest number x that is a divisor of both a and b. So the largest number which divides both the numbers a and b, that will be GCD of two numbers. For example, 6 and 9. What is the largest number that divides both 6 and 9? So does 1 divide 6 and 9? Yes. Does 2 divide 6 and 9? 2 divides 6 but doesn't divide 9. So divides 6 but doesn't divide 9. So it's not a GCD, not a divisor. Is 3 a divisor? Answer is yes. Is 6 a divisor? No. 9 a divisor? No. So what is the greatest divisor of 6 and 9? You can see it is 3. So can you tell GCD of 10 comma 12? What is the largest number that divides both 10 and 12? Or maybe like 20 and 30? What is the largest number that divides 20 and 30? You can see 5 divides. You can see 10 divides. Is there number larger than 10 that divides it? Answer is no. So GCD of 20 comma 30 is 10. So GCD, not that it need not to be limited to 2 numbers. You can define it for more than 2 numbers. So you can even say what is GCD of 20, 30 and 50. So then in that case, you will have to find number which divides all 3 of them. So what is the largest number that divides all 3 of them? So that is also 10. Fine. So at least definition of GCD is clear. So if using this definition, we want to write a code for finding GCD. So GCD by definition, let's say we are given 2 numbers int A and B. So we can iterate over all the numbers from 1 to. So what is the largest value of GCD? So let's say I will iterate over int x from 1 to x less than equal to something, and x plus plus if a percent x is equal to 0 and b percent x is equal to 0. I will say, even let's say I start from the reverse order, x from some large value, x greater than equal to 1 and x minus minus. If it divides, then I will say return x. Fine. And let's say here I will say return, or let's say assert false. Like this line is not supposed to be executed. So in this code, what should I be writing here at this place? So at this place, I should have x equal to what is the largest possible value of GCD. So can GCD of 2 numbers be greater than any of those numbers? The answer is no. So it cannot be larger than minimum of a comma b. So the largest number that you can try is minimum of a comma b. And then you can try from minimum a comma b till 1, and you check whether it divides both of the numbers. If yes, then you will say this is a GCD. You will directly return because you are going in the reverse order. So the number will always be largest. Fine. So let's try GCD of 20 comma 30 and see what does this program say. So okay, let's print this out. Just a second. So this program says GCD of 20 comma 30 is 10. So let's try something. GCD of maybe 1 comma 30. So 1 comma 30 should be 1. So let's see if that works. This one. You can try GCD of 30 comma 30. GCD of 30 comma 30. Fine, which is 30. You can try like some other cases. So this is the simplest program. So what will be like time complexity of this program? So what is time complexity of this program? This would be minimum of a comma b. So if a and b are very large, this program will not run in time. So let's say int a is equal to some 1e9, int b 1e9 is 10 power 9, and b is let's say 1e8, and I want to find GCD of this, GCD of a comma b. Let's see how much time does it take. So that third step, it took some time, but it's not like directly visible to us. So it took some time. You can see that so in system it's showing 0.03. So if you try like maybe slightly larger numbers, 1 9 or something. Okay, maybe like I should give some number as a prime. Let's say 1 9 and 1 9 minus 1. And let's see how much time does it take. So it took 0.283 time. So if you are given, so its time complexity is minimum of a comma b. So this program will not run fast if you want to compute GCD for many numbers. So let's say you want to find GCD for thousands of pairs of a comma b, then it will be difficult for you to do. So this is like the basic. So how can I make it slightly faster? So you can make one observation that GCD of a comma b, so the number which divides a and b, and suppose a is greater than b. Suppose a is greater or equal to b. Fine. I can always assume a is greater or equal to b. If it is a is less than b, I can swap, and then a will be greater or equal to b. So if a is greater than or equal to b, then GCD of a comma b will be same as GCD of a minus b comma b. So this identity is a very important identity. So it means that for two numbers, if you subtract one from the other, from the larger the smaller one, the GCD is still going to remain the same. It's not changing. So for example, GCD of 20 comma 30 will be same as GCD of 20 comma 10. So both the GCD is equal. And GCD of 20 comma 10 will be equal to GCD of 20 minus 10. From the largest number, subtract the smallest number, keep that as one number, and 10 comma 10. So what is GCD of two equal numbers? That number itself, because that's the largest number that divides itself. So this can be the case. So this is one example. So what is GCD of, let's say, 1 comma any number n? So what is the largest number that can divide 1? It's 1. What is GCD of 0 comma any number n? So every number divides 0 basically. So you can say its GCD would be n. Fine. So using this identity, we can write another code and get GCD. So let's say GCD, what do we give it name? By subtractive identity, let's say subtractive identity. And here I pass two numbers, a comma b. So you can implement this recursively, you can implement this iteratively as well. So let's try implementing it recursively maybe. So first, if a is less than b, we just swap a comma b. So this means at this step, a will be greater or equal to b. Fine. So I can do check if b is equal to 0. Then I can just return a. Otherwise, what can I do? I will do GCD of a minus b comma b. So this is your base case. So let's try GCD by subtractive identity and see whether it works for 20 comma 30, and we will see for other cases. So for 20 comma 30, say GCD is 10. Let's try some more example. GCD of 1 comma 30, GCD of 30 comma 30. So 20 comma 30 is 10, 1 comma 30 is 1, 30 comma 30 is 1. So let's try some interesting. Maybe. So maybe 17 into 3 is 51. And 17 into maybe 9, let's say 153. let's try this. So 51, 153 is of course 51. So let's try 34, 53. So this is 17. So 17 is the largest number which divides this thing. So is this function clear to everyone? Why this function works? Like if B, this is your base case, if B is equal to 0, then you are sure that GCD is going to be A, because GCD of 0, comma n is equal to 1. This is due to property that GCD of 0, comma n is equal to n. And this I am using the identity, this identity I am using this identity. This is using identity. So this is your recursive function. You can even make it an iterative function. So do the same thing till B becomes 0. So you can even make it identity. So let's see how much this program, what will be time complexity of this program? Is there any chat option where people can like comment or something?
Yes, Praveen, there is, just that they are not using, maybe they don't know.
Okay.
Yeah, there is.
Okay. So the time complexity of this would be, so let's see. So if you are trying GCD of, let's try finding GCD of 1, comma 10 power 9 and see how much steps it will take. So example is, so I'm calling this function with parameter 1, comma 10 power 9. So what will be value of a comma b? So let's print value of a comma b in each iteration. And I will call this for 1, comma, let's say maybe 1, comma 1000. 1, comma 1000. So in first step, a will be 1, b will be 1000. Then it will swap a comma b. A will become 1000, b will become 1. Then it will subtract 1 from a. So it will be, a will become 999 and this will become 1. Then it will become 998, 997. So it will be subtracted by 1 each time. So let's try seeing this. So let's call this. So a comma b, if a is less a greater than equal to b, so GCD of a minus b, 1, comma 1000. Is it compiled? A comma b, 1, comma 1000. So a must be greater than equal to b, a minus b. Okay, this is interesting. Oh, sorry, this is not calling this function. This should be calling this function again. So let's see this. So you can see that it called 1, comma 1000. Then it become 999, 1, 998, 997, 996, 995. So going so on so forth, keep going till 1, comma 1. Then this became 0, comma 1. Here it will become 0, comma 1. Then it was swapped. So it became 1, comma 0 and b is equal to 0. Then it returned a. So it took. So this code, in worst case, it may take here time complexity of order of minimum of a comma b again. Because if your a is very small, it will keep subtracting it one by one and it will take a lot of time. Fine. So this program is a step in maybe right direction, but this will not also work for a lot of test cases. So if I had like here, instead of 1 10 power 9, it will take 10 power 9 steps. So if I make multiple queries of this GCD comma subtractive identity, this won't run in time. So how can we make this function faster? So how to make this faster? So what you can do is you can see what this function is doing. So what does it do? So GCD of, let's say 20 comma, let's say 105. So this, or maybe like 105 comma 20. So in next iteration, it will make 105 minus 20, which would be 85, or let's say 10. Fine. So it will make 95 comma 10. Then it will go 85 comma 10. Then it will go 75 comma 10. 85. Then it will go 75, then 65, 45, 35, 25, 15, and 5. And then it will come to GCD of 5 comma 10. So can you see like all of these steps, what these steps do? So from the larger number, I keep subtracting 10 until the number becomes less than 10. So what does this operation mean? This operation means I am taking remainder of 105 modulo 10. So instead of this step, what I'm doing is 105 and keep dividing it by 10 till I can divide, and whatever remains is the final remaining number. So instead of going from GCD of 105 comma 10 to in single steps, I can directly go to GCD of 105 mod 10 comma 10, which is GCD of 5 comma 10. Fine. So this function gives rise to another identity or another property. Identity is same as property of GCD, which is GCD of two numbers a comma b. Let's say a is greater or equal to b. It's same as GCD of a mod b comma b. This is very important. So for example, GCD of 10 power 9 comma 1. What is GCD of 10 power 9 comma 1? It is same as GCD of 10 power 9 modulo 1. So what is remainder when you divide 10 power 9 by 1? So the remainder is 0. GCD of 0 comma 1. So what is GCD of 0 comma 1? GCD of 0 comma 1 would be 1. It won't be 0 because every number divides 0. So the answer would be 1. So you can see 10 power 9 comma 1 is 1. So the benefit of this identity is in the previous operation, you are subtracting b each time. Now in single step, instead of doing those subtractions, you will directly go to the modulo. So let's try the same function, writing the same code. Int, let's say GCD underscore final int a comma int b. Let's write the same code, and instead of so we call GCD final. So instead of a minus b, what should be the thing? It should be a mod b. Using the identity GCD of a mod b is equal to GCD of this thing. So let's try running GCD final and see what are values of a comma b. So in a single step, 1 comma 1000, it swapped and make it 1000 comma 1, and then in single step it went to 0 comma 1. So it did not took all those steps. Fine. So let's try some more examples and see whether it gives right output or not. So instead of this, I have to make GCD final, GCD final, GCD final, GCD final. So let's see. So for 1 comma 1000, the GCD was 1, and so this one is fine. So for 20 comma 30, the answer is 10. So in first step, A was 10, B was 20. The next step, this became 0, this became 10. 1 comma 30, the answer is 1. 30 comma 30, the answer is 30. 34 comma 153, the answer is 70. So this function that we have here, this function runs like considerably faster, and time complexity of this function is order of log of maximum of a comma b. So whatever are your numbers, so your numbers a comma b are, let's say, 10 power 9. So its time complexity is log of 10 power 9. So log of 10 power 9 is not that large number. So can you see what will be log of 10 power 9? Let's say base 2. So maybe we can do log of 10 power 9 by log of log of 2, I guess. Yeah. So this is approximately 29.8930. So for finding GCD of numbers till 10 power 9, it will take only 30 steps. So let's try running this program on some random numbers and check how much time it takes. So I will make, like, let's say 10 power 1000 iterations, and I will generate two random numbers and I will find their GCD. Random percent 1 9 plus 1. So this is one random number A, and let's say this is another random number B, and find GCD final of A comma B, and let's see how much time does this code take. And let's remove the debug statement. So you can see that this program run for finding 10 power 5 GCDs, it only took like 0.43 seconds. So this program is like so fast. And if I, instead of GCD final, if I try any other GCD, let's say GCD by subtractive identity, you can see that that will take considerably very large time. So sorry, it is first printing. So let's remove all the debug statements. See, so this time GCD by subtractive identity. Okay, this also seems to have taken, because random numbers, most of the, so one problem with random numbers is most of the random numbers have their GCD to be, most of the time they will be co-prime to each, or like their GCD will be either one or it would be like very, very small GCD. So let's try seeing its output. Debug of this. So most of the time you can see GCD is very small, 1 1 1 1. So instead of, let's take it to be 1, and now we can try doing the same and see how much time does it take. Int A comma B. Let's see why it is taking so less time. It should be taking slightly more time. This time set segmentation fault. 1 comma. Is this number last then? So this time it did not work. It's saying, let's see, make it 26. Again, it is giving segmentation fault. So most likely its segmentation fault could be due to the fact we are like going into recursion 10 power 9 times. So it will like blow up your stack, because this function is a recursive function. So it's going deep into the stack. So it will probably blow up your stack. So let's try with this very small number and see whether this one works fine. Yeah, this one works fine. But you can see it was taking a lot of time. So if we see this, you can see now it's taking like a lot of time, because its time complexity of this function, GCD by subtractive identity, is order of A comma B. So if you keep A very small and B very large, then it will take a lot of time. Fine. And this function GCD final is comparatively very fast. In fact, I am like not proving here why it is order of log of max of A comma B, but you can like assume that it is log of max of A comma B. If you want proof, then maybe I will just give few lines ki why this is log of max of a comma b. So what happens that in so in first step, let's say I have a comma b, then I will have a comma b. So this number a mod b. uh, So this number would be smaller than, if you do one more iteration, this number will become half of max of. So suppose here, a is greater than or equal to b. So in the next step, you will have, let's say a mod b is b. So in this step, so this is step 0, this is step 1, and this is step 2. You can prove that in the second step, the maximum number would be, so max of a comma b in this step would be half, would be at most half of max of a comma b in step 0. So suppose a comma b was, let's say 30 here, then you can guarantee that in this next step it would be 50. It cannot be larger than half. So in two steps it gets down by half. Maximum value of a comma b gets down by half in two steps. So this way it will, in log n steps, 2 times log of max of ab steps, this one will go, the max value will go till 1. So in two steps, the max of a comma b becomes at most half of the let's say, well, in two steps the value of max comma will become less than half of its original value. So let's say its value was 10 power 9, max of a comma b was 10 power 9. In next two steps, it will become 10 power 9 by 2. In next 4 steps, it will become 10 power 9 by 4, and so on and so forth. So this way you can see that in log of 10 power 9 times 2 steps, it will be, max of AB will become 1. And if max of AB is 1, in the next step itself, you will end the recursion. So that's why its time complexity is log of. So this fact, you can prove this fact. It's not like that complicated. You can prove this fact. It's like, it's kind of not that hard. But as of now, you can just remember the fact that you can write GCD program in this way. And instead of, so this modulo operator is important and other things are important. So this is about GCD. If anyone has any doubts till now, should I proceed to next topic, or anyone wants to ask something or have any doubt? Should I proceed, or like you want to ask something? So essentially, like, remember that this GCD do a mod b, and uh, remember that it's time complexity of just log of what is the maximum of a comma b. So if a and b are like very large, you can apply this algorithm and this can run really fast. Fine. So let's go to next topic, and here we will discuss like primes related thing. So let's copy paste this thing. And so, okay. So what is like a prime number? So a number is called prime number if it has no divisor other than 1, and let's say n. And so So this is like a slightly tricky definition, but a number is prime number if it does not have any divisor other than 1 and n. So number 1 is not a prime number, which is kind of like an exception to this definition. So you can adjust this definition in such a sense that you can make 1 not a prime number, but 1 is not a prime number. But you can see that 2 is a prime number. 2 doesn't have any divisor other than 1 and 2. So 2 is a prime number. Is 3 is a prime number? Yes, it is a prime number because its only divisors are like 1 and 3. Only divisors are 1, 2. Is 4 a prime number? No, because it has a divisor 2. Is 5 a prime number? Yes, because it only has divisors 1, 5. 6 is not a prime number. Why it's not a prime number? Because it has a divisor 2. So basically these divisors are called like non-trivial divisors. So for a number, trivial divisors would be 1 and the number itself. So for example, for 6, the number 2 is a non-trivial divisor. So if a number has a non-trivial divisor, then it will not be a prime number. If a number has non-trivial divisor, it won't be a prime number. For example, 6 is not a, for example, 10 is not a prime because it has 2 non-trivial divisors. Which are those 2 non-trivial divisors? You can see 2 and 5. It also has divisors 1 and 10, but those are trivial divisors. Like they are divisors by default, basically. So how can I make use of this definition and write a program to check whether a number is prime or not? So what do? I try over all possible numbers from 2 to n minus 1 and check whether any one of them divides or not. So I from 2 to n minus 1. So I iterate over all non-trivial divisors. Fine. So if n% I is equal to 0, then you will say return false. Otherwise, you will say return true. But remember, if n is equal to 1, this is not a prime. Fine. So let's test this program. Is prime basic of, let's say, 1. And let's try from 1 to, let's say, 10. 1 say n less than 10 and plus plus. Let's test how many of them are prime numbers. So you can see, let me print n comma this thing. Yeah. So you can see 1 is not a prime, 2 is a prime, 3 is a prime, 4 is not a prime, 5 is a prime, 6 is not a prime, 7 is a prime, 8 is not a prime, 9 is not a prime, 10 is not a prime. You can run it for like 100 and check which of the numbers are prime, which of the numbers are not prime. You can see 89 is a prime, 83 is a prime. You can see 51 is not a prime because 17 divides 51, 53 is a prime. So this is like very basic check for prime numbers. And what will be time complexity of this basic program? So what is time complexity? Would be order of n, where the number you are checking, not order of n square. You are iterating only over n numbers. So it will be order of n itself. So you can optimize it a bit by observing one thing. So this is very basic program. So let's make an observation. So the observation is, if there exists a divisor, so if a number is not a prime, then there will be a divisor whose divisor less than equal to square root of n. So if a number is not a prime, then there will always be a divisor whose value is less than equal to square root of n. So how can you prove this? So for example, let's say number is 51. So you see 51 is not a prime. So you will always find a number which is less than square root, you'll always find a divisor which is less than square root of 51. So what is square root of 51? So it is 7. So you'll always find a prime number which is less than 7. So you can see 3 into 17. 51 is equal to 3 into 17. So 3 is one of the prime numbers which is less than square root of n. So how can you prove this thing, that there will always be a divisor which is smaller than square root of n? So you can prove it using, so suppose n is equal to p times q. So you can see that p is greater than 1 and q is also greater than 1. Otherwise, p and q will become trivial divisors. Is this clear? P is greater than 1 and okay. So what I'm trying to say, that if a number is not a prime, then there will always exist a divisor whose value is no more than square root of n. So for example, in case of 51, 51 is not a prime number. So there will exist a divisor of 51 which is less than equal to square root of 51, which is 7. So there will exist a divisor which is less than 7. So for example, 51 can be written as 3,70. So you can prove it in following way. So suppose you find a divisor, let's say you have a divisor d, which divides n basically. So divisor is d, so d divides n. D divides n. So if d is less than equal to square root of n, my property is true by default. Because I was saying if number is not a prime, there exists a divisor. So if this condition is true, I am done. Otherwise, you can see the number n by d. If you divide n by d, this number is also a divisor. It's also a divisor of n. So for example, for number 51, you can see that number 17 is not less than square root of n, but if you divide 51 by 17, this number 3, this is also a divisor of 51, and this is less than equal to square root of 51. So take any divisor, so let me write its proof, then you may understand it well. So how can I prove this? So suppose a number n is not prime, then take any divisor, any non-trivial divisor d, if d is less than equal to square root of n, my property is satisfied and I don't need to do anything. I'm done. Fine? Because I'm trying to prove this. Otherwise, I can see that n by d, if I divide n by d, this number n by d is also a divisor of n. Because this number n by d also divides n. So what will be n divided by n by d? What will be n divided by n by d? This would be d. And now you can see that both, because here you can see, otherwise if d is greater than square root of n, now you can see that the number n by d cannot be greater than square root of n, because if n by d is, you can see d times n by d is equal to n, and if d is greater than square root of n and n by d is also greater than square root of n, then product of those numbers will become greater than square root of n times square root of n, which is greater than n, but the product is only n. So you can see n by d cannot be greater than square root of n. So your property is, so n by d, so divisor n by d satisfies your property. Fine. Is this clear? So the idea is you take any divisor, you either that number will be less than square root of the original number, or you divide the original number by that number, the remaining number will be less than equal to square root of n. Both of them cannot be greater than square root of n. That is the idea. Is everyone clear with the idea? So how can you make use of this? Int is prime, let's say is prime, let's say second version of int n. So what do I do? If n is less than, if n is equal to 1, what do I say? Return false. In fact, n equal to 0 is also false. So if n is, then what do I do? Instead of going from till n, I will go I times I less than equal to n. And if n% I is equal to 0, I will say it's not a prime number. Otherwise, I will say it's a prime number. Is this code clear? Is this code clear? I'm going till I into I is less than equal to n, which means I is a divisor. So this is equivalent to saying I is less than equal to square root of n. So I'm iterating over all the numbers. So let's compile this and try to. So this time 97 is a prime. Let's go for like smaller numbers and see till 10 only. So if 2 is prime, 3 is prime, 5 is prime, 7 is prime, and so on and so forth. So what is time complexity of this program? What is time complexity of this program? It will be order of square root of n. So for n equal to 10 power 9, approximately how many steps will it take? What is square root of 10 power 9? What is square root of 10 power 9? 10 power 9. So it is approximately 31,000. So it will take 31,000 steps. So if you were using earlier algorithm, it would have taken 10 power 9 steps. Now it will only take like 31,000 steps. So this is like much faster than original. Fine. So suppose I want to check. So let's say I want to find all prime numbers from 1 to, let's say, 10 power 6. So if I use this program for finding a single number n, it will take square root of n steps. So you can say in the worst case, finding single number is square root of 10 power 6. So you can say it will take approximately 10 power 6 times square root of 10 power 6. So what is 10 power 6 times square root of 10 power 6? 10 power 6 times, what is square root of 10 power 6 is 10 power 3. This will become 10 power 9. So yeah, so this program may not run in time. So suppose instead of this, I had, let's say, till 10 power 7, 10 power 7. So this number is like much larger. How much is it? 10 power 7 times square root of 10 power 7. This number is 31 into 10 power 8, I think. Yeah. 3 into, I can see key 3 and 6, 9. So 31 into 10 power 9. So this is 3 into 10 power 10. So this one is definitely won't run in time. So if someone asks you, find out all the prime numbers from 1 to 10 power 7, you cannot do something like this. Int max equal to 10, let's say 1 is 7. And I do for int I n equal to 1, 2, and less than equal to max n plus plus is prime second version of n. So let's count all the prime numbers. Let's say count equal to 0. If this is a prime number, I will say count plus plus, and now I will just print the count, let's say. So this program will find out how many prime numbers are from 1 to 10 power 7. So this one is taking a lot of time. So let's try running the same program from 1 to 10 power 5. This one runs pretty quickly. It says that till 10 power 5, there are 9,000 prime numbers. Okay, let's try 10 power 6. So from 10 power 6, it's saying that 78,000 prime numbers. So this is running, it took slightly more time. It took 0.474 time. You can try, let's say 5e6. And you can say that it starts taking quite a bit of time. It took like 2 seconds. For 1e7, I think it will take even larger time. Let's say how much time it will take. Yeah, it took like 5 seconds. So if you have to do it in 1 second, you won't be able to do. So let's learn an algorithm which can solve this problem in much faster time. So let's go to that. So that thing is called Sieve algorithm, Sieve of Eratosthenes. Sieve of Eratosthenes. So I may be wrong in the name of Eratosthenes. So apologies to Eratosthenes in that case. So do you know what is a sieve? I don't know. Yeah, I could be misspelling. Is that the spelling? S-I-E-V-E or S-E-I-V? Yeah, I was right. S-I-E-V. So sieve is basically this chalni. So you will get to understand like why it is called sieve, why this algorithm is called sieve. Fine. So let's see. So what do? You write down, let's say, all numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then maybe 11, 12, 13, 14, 15, 16, 17, 18, and let's say 19, 20. So you start with number 2. So what do? You cross out all the numbers that are multiples of 2. And you say that those numbers are not prime. So you start with 2, you say this 2 is not a prime, this 2 is not a prime. Whatever are the multiples of 2, you can see that those won't be prime. So 2 is a prime, fine. But whatever is multiple of 2, those numbers are not prime. So 4 is not a prime. 6 is not a prime. 8 is not a prime. 10 is not a prime. 12 is not a prime. 14 is not a prime. 16 is not a prime. 18 is not a prime. And 20 is not a prime. Okay. So you go from left to right. You start from number 1. You start from number 2 because you know number 1 is not a prime. So you forget number 1. You start from number 2. Number 2 is a prime. Then you go over all multiples of 2 and you mark them to say not a prime. So for 2, you can say that 4 is not a prime, 6, 8, 10, 11, 12, 14, 16, 18, and 20 are not a prime. Then you go to number 3. Number 3 is a prime. Then what you do, whatever are the multiples of 3, mark them as not a prime. So what is multiple of 3? 6. This is not a prime. This is already marked. What is multiple of 3? 9. So you say 9 is not a prime. Then 12. Then 15. Then number 21. So 21 is not a prime. So on and so forth. Then you go to 4 and you see 4 is not a prime. So you don't need to do anything for 4. So you go to number 5. So 5 is prime. Then you mark out all multiples of 5. So you mark 10, 15, and then 20 and so forth. So what is the idea? So let's say so you can understand this algorithm as follows. So let's say you have a sieve. Let's say you have a sieve. Sieve is basically chalni, which originally contains all primes. Fine. All numbers. Which originally contains all numbers. So 1 to, let's say you want to find 1 to 21. What are the primes? So for example, let's say 1 to 21. So originally in your sieve, you have all these numbers. So what you do, you remove number 1 in the beginning itself, because number 1 is not a prime. So let's say you have from 2 to something. So what you do, you find the smallest number, and you are guaranteed that the smallest number is prime. You are guaranteed that this number is a prime. The smallest number is a prime. In our first case, the smallest number will be 2. So then what do? You remove all the numbers which are multiple of 2. Remove all the numbers that are multiple of 2 from the sieve. So basically what did you do? You kind of like, whatever were multiples of 2, you kind of removed them from your chalni basically. So remove all the numbers that are multiple of 2. So what are multiple of 2? Except 2. Multiple of 2 except 2. Because 2 is a prime. Don't remove prime. Whatever are non-primes, you kind of want them out of your sheet. So you removed 4, 6, 8, 10, 12, 14, 16. So you removed 16, 18 and 20. Now what numbers? So now the numbers are remaining from 2 to 21 except these multiples of 2. So what is the next smallest number? Find the next smallest number. Smallest number which you haven't picked till now. So the first smallest number you picked was 2. So what is the next smallest number that you did not pick, that you did not consider? So what is the next prime? So that number is 3. So now you remove all the multiples of 3 from the sieve. Remove all multiples of 3, which are 6, all the multiples of 3 except 3. So 6, 3, 9, 12, 15 and 18 and 21. So you remove all these numbers. Now what number is remaining? So now 2 is remaining, 3 is remaining, 4 is not remaining, 5 is remaining, 6 is not remaining, 7 is remaining, 8 is not remaining, 9 is not remaining, 10 is not remaining, 11 is remaining, 12 is not remaining, 13 is remaining, 14 is not remaining, 15, 16, 17 is remaining, 18 is not remaining, 19 is remaining. Is 20 remaining? No, 21 is also not remaining. So now remaining numbers are this. So you have picked 2 and 3. Now you pick the next smallest number. So that is 5. So 5 will be prime. So you cross out all multiples of 5. So cross all multiples of 5. 5 except 5. So which means you cross out 10, 15, 20. But you see that already 10, 15, 20 are crossed out. So similarly, now you will try with 7. Remove all multiples of 7. So you will see that all multiples of 7 are already removed. So in the end, whatever is remaining in your sieve, whatever is remaining in your sieve is just the prime numbers. So let me write a pseudocode for this, and then we will see whether you get this idea or not. So let's say int n. So I want to check whether a number is prime or not for numbers 1 to n. So what do? I create, let's say, a vector of Boolean of prime sieve. Let's say prime of is prime. Let's call p of n. That's a mark of n. So initially I say all the numbers are prime. Initially all the numbers are in my sieve. So I'm saying all the numbers are prime. So for int I is equal to 0, I from 2 to n, I plus plus, mark of I is equal to true, or let's call it h prime maybe. Is there a function h prime? Yeah, h prime is fine. So this is like your sieve before starting. Before starting, I have taken all the numbers from 2 to, let's say, n. So I've taken all the numbers from 2 to n, and they are in my sieve. So sieve contains only the prime numbers. So then I go from 2 to n, And if this number is prime of I, then I will go over all multiples of I. So what do I do? For int so j are multiples of I. So I'll start from 2i, I plus I, and j less than equal to n, j plus equal to I. So this is going over multiples of I. And I'm saying each prime of j is false. So these numbers are not prime. So finally, what do I do? Now, for whichever number each prime of I is true, those numbers are prime. So for example, if I have to count, so let's try this. Let me just print all the thing less than equal to ni plus plus. If each prime of I will let's say debug I, just I will output those numbers. So let's try Sieve for 10 numbers. Sieve for let's say 20 numbers and see what happens. So you can see 2, 3, 5, 7, these numbers are here. So let's see in individual steps we will see what is happening. So this is I. So this is let me see out the smallest number in the sieve, smallest prime number in the sieve that is not considered yet. Considered yet would be I, fine, and these will be multiples of I. So these j, see out j, let's say see out on the fly. So these are multiples of I, and let's see. So let's say, so in the first step, the smallest number that is not considered yet is 2. So 2 is a prime. So I am going over all multiples of 2, which are larger than 2, 2, 4, 6, 8 till 20. And I'm saying they are not a prime. Now I'm going all multiples of 3 and saying 6, 9, 12, 15, they are not prime. Then I'm going over multiples of 5 and saying they are not prime. Then I'm going over multiples of 7, saying they are not a prime. So I will iterate over all the numbers that are part of my sieve and will remove the multiples of the smallest number that is not considered. Is the idea of sieve clear? If anyone has any doubt in like what is the algorithm, can you at least like get the idea of what the algorithm? Why 7? We have already discarded 14. So we have to consider all the prime numbers basically. So 7 will be considered because 7 is a prime number. So in the sieve, I have prime numbers. So basically, you can kind of think like sieve is your like chalni. So in your chalni, you have prime numbers, and you are picking one number that you are sure to be prime, and whatever are its multiples, you are filtering them out of your sieve, and you try this process again and again. So you take one number that you haven't taken till now. So you take that number, whatever are its multiples, you are guaranteed that they are not prime. So remove them from C. So keep doing this step till you can find a prime number which you haven't taken yet, and take all its multiples and remove them. So in the end, what will happen? All the numbers that are remaining in your sieve will be your prime numbers only. Is that clear? Okay. So let me just like comment this out. Let's try running this program for n equal to I can, instead of printing this, let's print count. Okay, how many numbers are prime, and debug, let's say count. So let's run sieve for 10 power 7, 1 is 7, and see how much time does it take. So it took 1.192 seconds. And how many, sorry, there's something wrong because count is 0. So we are doing some mistake. So it should be count plus plus. Let's see how much time does it take. So it is saying 6, 6. So let's match this number with this also. So this is our like other function. So let's say max is equal to 1 is 7. So from the sieve method, this is 6, 6, 4, 5, 7, 9. And from the other method, it is also the same. And you can see that if I don't have this much, this is taking like, this is taking like 1 second. And if I use the second method, that will take, I think, 4 seconds or something. So this, the square root n method directly is taking like 5 seconds. So it is like 5 times faster for 10 power 7. This gap will become larger and larger if you try for larger numbers. So suppose you want to try for, let's say, 3e7. Let's try for 3e7 and see how much time will the sieve take. So for 3e7, it is taking like 2 seconds. But if you try the other program for 3e7, it will take maybe like 10 seconds or something. So the gap will be more and more. So let's find the time complexity of sieve method. Time complexity. So its time complexity for finding n numbers is n log n, and we will prove this in some time. But you can remember that its time complexity is n log n. So for 10 power 7, how many steps will it take? 10 power 7 times log 2. So this one doesn't have log 2 function. So let me just go to Python maybe. So 10 power 9, 10 power 7 times log 2 of 10 power 7. Log 2 is not defined. So this is bad. Yeah, so math dot. So this becomes approximately 336, 2 into 10 power 8. So this will run in like 1 second or something. So it is making like 2 into 10 power 8 operations. So n log n, you can see, is considerably faster than n square root of n. Which one is faster? N log n or n square root of n? You can see n log n is faster because log n grows much slower than square root of n. Because for n, but square root of n is 30,000. So square root of n is even faster. So its time complexity, like you can assume it to be n log n. There are like n log n is not like a proper bound. You can have even better bounds than this. But for all practical purposes, you can assume it to be n log n. So don't go over like n log of n. So I'm not, so basically like, because order of n log n means that it will take in the worst case n log n time. So you can even find better bounds. You can say it will take order of n of some other function also. So some people say that it is n of log of n. So I'm not sure about that, but you can, at least I can prove that its time complexity is n log n. Fine. You know that I can say, so how do I prove this? So how many steps will it take? So for each I, how many steps will the inner iteration take? So it is going over all multiples of I. So for a single I, for a given I, for a given I, how many multiples can be there till n? So, so you can see there can be at max n by I multiples. Because I into 1, I into 2, I into 3, I into 4, till I into n by I, which will become equal to n. So the inner loop can run at max n by I times. So this loop, j equal to this loop will run at max n by I steps. Is this clear to everyone? This fact is very important, like why it is running till n by I. Because you are going over multiples of I. So how are you going? So you are going I into 1, I into 2, I into 3, till I into n by I, which becomes equal to, which is the largest number. So if you go I in, if you take number larger than n by I, so you take, let's say, n by I plus 1, your number will become greater than n. So you don't need to go till that point. So you are going till n by I steps only. So can I say that your time complexity is n by 1 plus n by 2 plus n by 3 plus dot 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 plus n by n? Can I say that? Because for each I, I'm going at max n by I times. So you can say your time complexity is for I equal n by 1 plus n by 2 plus n by 3 plus n by n. So this one, can I say? Time complexity equal to this. Is this expression, everyone like clear with this expression? What is this expression? Why this is true, the time complexity will be this. In fact, this will be n by p, where p is prime. This will be n by 2 plus n by 3 plus n by 5 plus n by 7 plus so on and so forth. So in fact, this will be n by sum of n by p, where p is prime. But we can, so we can even omit saying that p is prime. We can take all the numbers and try finding a bound, because that bound will be larger than this sum of n by p when p is prime, because we are considering extra numbers only. So let's take this expression. Let's call, what I can do is I can take n common from this. Now I have gone into domain of real numbers. So it will become 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus dot 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 plus 1 by n. Fine. So this is my time complexity. Let's call it TC, time complexity. So can you find a bound over this number 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5? So this series is called harmonic series. So you can find a bound over this. So you can assume it like this: ki harmonic series is bounded by log of n. So we can kind of like try. So harmonic series sum is bounded by order of log of n. So if you try very large n, so let's try this up. Double harmonic int n for I equal to 1, let's say n, for I is equal to 1 to I less than n, I plus plus answer plus equal to n by I. Let's take it double, and let's say double answer equal to 0, return answer. And let's try finding what is harmonic of 10 power 9. We will get an idea ki how large is this number. Harmonic of 1 in 9. It will take some time to run, but it will, in the end, it will give some number, and we can see ki how large is that number. We did not print it out. Let's print it out. So harmonic of 1 in 9, it will take some time, and in the end, it will output the value. Okay, so this value, in fact, harmonic was 1 plus 1 by I. It is multiple of this thing. So let's try that. So 1 plus 1 by I should be pretty small. This is only 21. So you can see that this number, this harmonic number, this number is pretty small. In fact, this number is bounded by log. So this number will not be greater than log of n. So this harmonic series, its sum will not be greater than log of n. And you can see that your time complexity is n times harmonic sum, n times harmonic sum of n. And you can see that harmonic sum of n is a really small number. It's not that large number. It's bounded by log of n. So you can see that your time complexity is n times log of n. Is that clear to everyone? Like I did not prove that for harmonic sum, the sum of the harmonic sum is bounded by log of n, but I gave you an intuition that see this harmonic sum for really large number, it's very small. So I did not prove, but you can at least get an intuition that this number is in fact very small. This number is not that large. You can prove it formally as well, but like, in fact, if you want to prove this, maybe I'll spend just a second. You can say that this number is integration of 1 by x dx. So this number, harmonic sum of n would be less than integration of 1 by x, or limits will be, and let's say limits, where limits are from 1 to n. Because this 1 by x times dx will be larger, because these numbers 1 by 1 plus 1 by 2 plus 1 by 3, these will be in integration already. So this integration will be larger. So what is integration of 1 by x? Integration of 1 by x is ln x. And if you put limits, it will become ln. So this will be ln x. Limits are from 1 to n. So you can say ln of n minus ln of 1, which is ln of 1 is 0, so ln of n. So this sum, harmonic sum, is less than equal to ln of n. Did you get this idea? If you want me to explain, I can explain you further. Like at least to get this idea, that harmonic sum of n will be less than this integration, because this integration contains the points 1 by 1, 1 by 2, 1 by 3, 1 by 4. It contains all the real numbers, but it at least contains 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by n. Do you get this part, that this integration will be larger? So you can see like harmonic numbers, even if you do 1 by 1 plus 1 by 1.1 plus 1 by this. So if you keep going this for all the real numbers x from 1 to n, that sum itself is bounded by ln of n. So that sum is ln of n. So this harmonic sum will be ln of n. So do you know difference between ln and log? So ln is called like natural log, and it's just that its base is e. That's the difference. There is no other difference. Okay. Instead of 2, the base is some number 2.71 some transcendental. Right. Okay. So this is Sieve algorithm. Its time complexity is n log n, and you can use it to find all the prime numbers, which are okay. So let's do one more thing. uh, just quickly divisors. Let's see quickly. Uh, let's say I want to find divisors of some number n, and number n is, let's say, from 1 to 10 power 9. So how do we find divisors of a particular number? We can further optimize, but let's not waste time there, because it doesn't. If you know this much, if you understand this much, you are good to go for like all your cases. You don't need to like really further optimize. N log n is a really good NFBOM. Do anyone wants me to repeat anything in this prime sieve part? Should I proceed further? If you have any doubts in proof, or you have, at least you should understand that how to write this prime sieve. You can see the implementation, how to implement this, and then you should also maybe reason, if you cannot reason out why its time complexity is n log n, at least remember that its time complexity is n log n. Is this clear? Anyone wants me to go over any part that is confusing or something? If something is not clear and anything that is not clear, let me know. I will be happy to explain. Does everyone understand? If I ask you to write Shiv without looking at this code, will you be able to write? And notice one thing. So what are like important steps in this Shiv? It's pretty simple. Initially, you mark all the numbers prime, then you iterate over all numbers, whatever are primes. You go over all their multiples and mark them non-prime. And notice this I plus I. So I shouldn't do j equal to I, because I have to mark all the numbers except I. So the first multiple would be 2i. So this should, you should take care. Rest all is fine. Okay, so let's go over the same thing for divisors quickly, and then we will maybe proceed to a few more things. Suppose someone asks you, find all the divisors of a number n, and n is, let's say, till 10 power 9. So what is like the simplest algorithm? What is the simplest algorithm? You go over all numbers from 1 to n and check whether it divides or not. If it divides, it's the divisors. Fine. In fact, let's do one thing. Instead of finding all the divisors, let's say count the number of divisors of number n. Number of divisors of a number n. Fine. Where n is less than 1 to 10 power 9. So let's write brute force. Fine, we'll write brute force quickly. What do you do? Int answer equal to 0. Then for int I is equal to 1, say I less than n. If n% I is equal to 0, you say answer plus plus, and then you say return answer. So this is your brute force. What will be time complexity of this program? Order of n. Is this clear? Is the brute force program clear? So if I ask you how many divisors are there for number 12, sorry, how many numbers are for, how many divisors are for number 12? Can you tell me in the comment section? Till my program calculates it, can you tell me how many divisors does the number 10 has, and check whether it matches or not? So 12 has 6 divisors. You guys are right. So what are the, like, what is the other way? You can count divisors using prime factorization as well. Prime factorization of a number of n. So what do you mean by prime factorization of n? So what do you do? Prime factorization of n would be p1 power, let's say, e1 times p2 power e2. So basically, you decompose this number n into prime powers. So let's say your number is 12. What will be its decomposition? How can you write it? 2 power 2 times 3. You can write it as following this. How can you write, let's say, 20? You can write 2 power, let's say, how can you write 60? Or maybe 180. So you can write 180 following way. How many powers of 2 are there? So 2 into, let's divide it by 2. So remaining is 90. And 2 into, so remaining is 45. So 9 into 5 into 3 into 3. Is this fine? So 180 can be written as 2 power 2 times 3 times 3 power 2 times 5. So this representation is called prime factorization of a particular number. So for a given number, how do we find its prime factorization? Can you tell me? In 10, can I do it in square root of n time? Yes. So how can I do? I go over all the numbers that are its divisors. Fine. And I keep dividing by that number. So basically, let's see. So for int I is equal to 2i into I less than n, I plus plus. If n% I is equal to 0, then I know that this, instead of I, let me make it p into p into p. So p, if n% p is 0, then I know, what do I know? That p divides n. So p might divide n multiple times. So let me just keep dividing n by p till it is divisible by p and e plus plus. So let's say vector of pair of int comma int prime, let's call it answer. So here you can do answer dot pushback. You can do p comma e. And in the end it, so till what, so p goes till square root of n. What if, so in the end, if n is greater than 1, it means that n is also a divisor. So answer dot pushback n comma 1. So this may not be clear a bit. We will just try running this program and we will see. Find prime factorization of 12. So let's see. Program. Find prime factorization of 12. N% p and divided to p e. Answer. Void. Okay, so 2, prime number 2's power is 2 and 3 power is 1. So let's try with it with 180. And it should be 2, 2, 3, 2 and 5, 1. 2, 2, 3, 2 and 5, 1. Let's try it with 17, a single prime number itself. And this is 17, 1. So let's try understanding what this program is saying. So you can see its time complexity is square root of n because p is only going till square root of n. Fine. It will not take more than square root of n. So what is happening is, if p divides n, then it means p is divisor. So you keep dividing n by p and you find out how many powers of p are there in n. So here I am finding, here e denotes how many times, how many, like what is power of p in the prime representation of n? Denotes the power of p in the prime representation. Fine, in the prime factorization. Because, so I am saying p comma e, I am pushing back. Why I am doing this condition? Because it might happen that in the end, n is remaining, and this n will be a divisor of the origin n, and I should make sure if this n is greater than 1, I should push this. Because suppose I don't do this, then what happens in case of 17? Let's see. Then it's saying empty, because there was no number which was dividing 17 till square root of n. Only number 1 was dividing. So you should make sure to handle that case. In case this remaining number is greater than 1, then you should also push that number. So this is your prime factorization. This thing. So this is 17 comma. So suppose I give you this prime factorization. Can you count how many divisors will be there using this prime factorization? Did everyone understood how to find prime factorization? Everyone understood this code? If anyone wants me to explain anything, let me know. Once more. Okay, which part is not clear? Uh, so, okay, while loop is not clear. So yeah, so this is so basically this number. So let's say n was 180. Let's try running this program in case of 180, and we will. So what do we debug? So debug prime p, and let's also debug e. Let's run this in case of 180 and see what is happening. So initially p is 2, and then it is trying to find how many times power of 2 are in 180. So it divides 180 by 2 once, the output is 90. It divides once again, it is 45. Now it is no longer divisible. So it determines that the number 2, the power of 2 is 2. So E is equal to 2. So it determines that the power of 2 in 180 is 2. So you can write 180 equal to 2 power 2 times something. So this it determined till now. Now it goes again that it will try it with larger number. And you can see that the way I'm doing this, you can see that this P will always be prime. P will always be prime. The way I'm running this for loop, you can see that P will always be prime. Because whenever I'm finding a number P that is prime, I'm removing all the occurrences of that prime from the number n. I'm dividing n by p till I can divide. So I'm removing all the powers of p from that number. So then what will happen? It will go, then in the next loop, p will become 3, and in 45, it will find powers of 3. And you can say that it powers of 3 is 2, and it will push back. So if you want to see, let's see for 540, and you can see that power of 3 is 3. Power of 2 is 2, power of 3 is 3. So if you don't divide n by p, then it might happen that in the next iterations, so what will happen? You cannot guarantee that the next number is going to remain. So the next p that comes in iteration, that may not be prime. Is that fine? Because suppose I don't divide, I don't do this. Instead of doing n by p, let's say I take another variable, m is equal to n, and I do this thing, m percent equal to p, m divided. So this way I can also find like occurrences of p. This is fine. So here, then if I check whether p is prime, you will see that, and let's print p. Let's see what happens there. Then you can see that you are finding all sorts of p. You are finding 12, you are finding 10, you are finding 18, 20. You are going over non-prime numbers as well, because from that number n, you did not remove powers of p. So those powers of p, so then the number p that is coming, that p will not be a prime number, because you did not remove any occurrence of prime from that. So if you remove all the occurrence of prime, then the next number you are iterating will definitely be prime. So if you do this, you can see that in each iteration, this p, let's only print p. This p is guaranteed to be a prime. P is 2, P is 3. Let me try like even larger. Into 5 into 7 into 13 into 17 into 21 into 23 into let's say 97 into 103. Let's try this. I just hope that it's not very large. If it is very large, then it will be a problem. I think it is probably become outside the limit of integer. Let's see how large is this. Yeah, it become outside the limit of integer. So let's remove something from it. Let's see this, whether this fits in integer. Yeah, this fits in integer. Or so this is bit weird. 97 is 101 prime. I think it is still an overflow. So let's remove few more things. It's still saying overflow. Let's remove a few more. It's not an overflow now. So you can see it is iterating over 2, 3, 5, 13, 17, 97. Each of them are prime. So is this fine? Like in this iteration, why it is important to keep dividing? Because that will ensure that each time I'm dividing, the remaining number P is a prime. So given a prime representation to you, how do you find the number of divisors? How do you kind of count number of divisors? So if number 180, so for 12, prime representation is 2 power 2 into 3. So how many divisors does 12 has? Can you use some combinatorics to get this answer? How many divisors will be there? So, okay. So you can see that the divisor of 12 will be of form this 2 power x times 3 power y. Jahan pe where x cannot be larger than 2. X can be 0, x can be 0, x can be 1, x can be 2. But if x is 3, then you are sure that it cannot divide 12. So where x is less than equal to 2 and y is less than equal to 1. Is this whatever did I told just few minutes back, is it clear to everyone? The divisor of 12 will be of form 2 power x times 3 power y, where x has to be less than equal to 2 and y has to be less than equal to 1. Is this clear? That so let's say, so you can see that 6 is a divisor of 2 and you can write 6 as 2 times 3. So in this case, x equal to 1 and y is equal to 1. Can x be negative? No. The smallest possible value of x is 0. So how many numbers are there? How many pair of x comma y are there where x is from 0 to 2, y is from 0 to 1? So how many pairs of x comma y are there such that x goes from 0 to 2, y goes from 0 to 1? You can see that x and y are independent. So how many values x take? X can take 3 values, 0, 1, 2. How many values can y take? 2 values, 0, 1. So how many pairs of x comma y can be there? 3 times 2. You can choose any one value of x from 0, 1, 2 and any value of y from 0, 2. So 3, 2 is equal to 6. Is this part clear? How many pairs of x comma y are there with this condition? Is this part clear? So if your number n has prime representation of p1 power e1 times p2 power e2 times, let's say, p3 power e3 times p4 power e4, can you tell how many divisors will be there? Can you find a formula for that? Maybe let's make it slightly smaller. Let's just do this thing. Will it be e1 times e2 times e3 or e1 plus 1 times e2 plus 1? It should be e1 plus 1 times e2 plus 1 times e3 plus 1. Dot, dot. Did you get this? Don't forget plus 1 part. Product of all the exponents plus 1. Okay, so let's implement this. So in this case, this was prime factorization. And let me change the same code. Find count divisors. Count divisors int n. So what do I do? Let's say return answer from here. Let me remove debug. Let's say its output is vector of int. So what do? I first find prime representation. Prime rep is prime representation of given number n. Now what do? I go over this prime representation and answer, let's say answer is equal to 1. The answer will be multiplied by second plus 1. So second gives me exponent. Return answer. Is this clear? This count divisors function. So let's see this function. Debug count divisors of, let's say, 112. And let's remove this part. So count divisors of 12 are 6. So what was its prime? So this will print the prime representation. So let's print the prime representation. So prime representation, let's remove some extra debugging. So let's remove this debugging. Let's remove this also. You can see that divisors are 2, 2. Like its prime representation is 2, 2, 3, 1. So you multiply 2 plus 1 times 1 plus 1. What will be time complexity of this count divisors function? What will be time complexity of this function? Order of, can anyone tell what will be time complexity of this function? Order of, what will time complexity of find prime factorization of n? Order of square root of n. Or whenever someone asks you time complexity, always tell it in terms of input. So tell in terms of n what is the time complexity, because the input of this function is n. So in terms of n, its time complexity of is order of square root of n. So this is one way. So now let me just move it to right place. If anyone has any doubt, let me know. Before proceeding further, let me know. I'll be happy to answer. Does anyone has any doubt in whatever I have told till now? So suppose someone, another way of like, so Now someone asks you to print all the divisors. So this time we counted all the divisors. Now if someone asks you to print all divisors of n, then what would you do? Now this is interesting. So how will you do that? You first find the prime factorizes this prime representation, p1 power e1, p2 power e2, and then you do a recursion to select ki how many powers of first prime will you select, how many powers of second prime you will select, and so on. Do you want me to implement that? Ki how to print all divisors? So a recursive function to print all divisors of n. Will you be able to do this? Ki how to find all divisors? Or should I implement it quickly? Do you at least get the idea ki how do you do? So let's say void print all divisors of int n. So the idea is as follows. So first you find the prime representation. Fine. So I found the prime representation in order of square root of n. Now over this prime representation you do a recursion. So recursion. What do you pass in your recursion? You pass this prime representation. Am I audible? Hello?
Yes, you are audible.
Okay. So everyone is able to follow till now ki recursive function to print all divisors. So if anyone wants me to repeat anything, don't hesitate. I will be more than happy to kind of repeat over that thing so that you can get an idea. So now I have to write a recursive implementation. So what is this? So this is p1 power e1 times p2 power e2 and so on and so forth. So now what should I do? I will select first prime power from 0 to e1, then from 0 to e2, from 0 to e3 and so on and so forth. And I will generate a number that I will call my divisor. So let's call recursion. So in recursion, I'm going to pass this array. So this is a vector of pair of int comma int. So I'm going to pass a reference to this. So let's call it prime rep. What other parameters should I pass in recursion? So I should pass at which position I am. Fine. And what is the number that I have generated? The number D, which is the divisor. And at the end, I should insert them into a list of divisors. That is answer. So let's say vector int answer. So yeah, I will call it prime rep. Index initially will be 0. D will be 1. Answer would be answer. And then I will print answer. So here, if index is equal to prime rep dot size, I mean, I have reached till the end. So I add this D to my answer. Otherwise, what do I do? So otherwise I take, let's say E1. So this E1 would be int E1, let's call it E, would be prime rep of index dot second. Fine. Now I will go from, I will choose power of, and let's say this called PB prime rep of index dot first. So I'll choose power P of X, P power X, where X is greater than 0 and X is less than E. So for int X equal to 0, X less than equal to E, X plus plus. So what do? I do recursion of prime rep index plus 1, D will be D, and answer would be answer. And here what do? Multiply D by P. So you can see if x equal to 0, I am not multiplying d by p at all. Then if x equal to 1, I am multiplying p by p once, then by p twice, then p by thrice, and so on and so forth. So if I do it x times, it will be x will go till e. So this is, let's try running this program, print all divisors of 12. Divisors of 12. So it says 1, 3, 2, 6, 4. These are how many divisors? 6 divisors. So is this function clear? This part is important. Even like if you don't get this line, so what this line is doing, it's just it's just a clever way to, at this point, I am multiplying d by p power x. So when x equal to 0, I'm not multiplying d by anything. But when x becomes 1, I will have multiplied by 1. X equal to 2, I multiplied by 2, 3, and so on and so forth. So in the end, this will be your divisor. So now you can see that prime factorization is this, and divisors of 12 are 1, 3, 2, 6, 4, 12. You can notice that these divisors, they are not in sorted order. So if you want them in sorted order, you should sort this array manually. How many divisors are there? You can see there are like 6 divisors. Is this clear? Is this part clear to everyone? If anyone has any doubt, let me know. This recursion is like so important that you will most likely find some problem in interviews related to this. So this recursion is very important. This kind of recursion is used in like many problems. Like generate this thing. Someone will say print all strings with some property, or like so this kind of recursion is very important. Someone will ask print all permutations, print all combinations. In all those sort of scenarios, this sort of recursion is used heavily. So you should understand how this recursion is working. So in each step, it is choosing p power x and is multiplying this d by p power x, and it keeps on doing till index become this thing, and whatever number comes in the end, that number comes out to be a division. So this recursion is very important. Make sure to like understand this. Anyone has any doubt in this recursion process? Any doubts? Anyone has any doubts, wants to ask something? Anything is, if anything is unclear, feel free to ask. Which part should I explain? All part. This is interesting. So is this clear? Like, do you know, find prime factorization of n. This will give you p1 power e1 times p2 power e2 and so on and so forth. So its output will be an array of this kind, 2, 2, 3, 1. So this will be your prime representation. So this is clear. So now in the recursion, so this prime rep and answer, these are, I'm just passing as a placeholder. Because the value of prime representation and prime representation is not changing. So this is just nothing. So this index tells me at what position I am. So initially I'm at position 0. So what this recursion is doing, so you can see that my divisor will be of form p1 power x1 plus into p2 power x2 times, let's say there are only k power xk. Is this clear that your division will be of this form? Fine. So in first iteration, when index equal to 0, I am choosing x1 from 0 to e. So x1 can go from 0 to e1. If your prime representation is p1 power e1, then x1 cannot be greater than e1. So the x1 will go at index 0. X1 will go from 0 to E1. And so suppose initially your initial divisor is d equal to 1. So you will multiply d by p1 power x1, where x1 will go from 0 to E1. When you go to index equal to 1, you will multiply d again by some number. So this d into p1 power x1, you will multiply it p2 power x2 till you reach the end. So you says if your size is k, so you'll reach at position k plus 1, and then this line will be executed. Answer dot pushback. This line will be executed when you reach at the end of the prime array. So then whatever is your d will be a divisor of your number n. So let's print this debug index comma d and see what is happening. So I'm starting with index 0 and d is 1. Then I will go to, and let's do one thing. Execute 0 say. Okay, let's do one thing. I will do debug index d comma. Yeah, let's do debug index comma d. And okay, so at index 0, you can see I started with 1, and then I went to index 2 again with 1, and then I went to index the next index. So I should also print here. So for I is equal to 0, initially d is 1. So it came here, index was 0, d was 1. Then it will go into this recursion. So index will become 1, and d is still 1. So then it will come again and again. So let's just do this small example. Let's run this for 6. You will get a better idea what is happening. For 6, what is happening? You started with I is equal to 0, d was 1. So you are at, you are printing here, I is equal to 0, d is 1. Then you call this function with index plus 1. So index will become 1. Index will become 1, and it will come in, and d is 1. So index is 1, d is 1. Then you come again here, and then again x equal to 0. Index is 2, and d is equal to 1. So index is 2, d is equal to 1. So your 1 is your answer. So at this point of time, you will insert 1 in your answer. Now you go back to the previous place, this 0, 1, and you multiply d by p. So you multiply d by 2. So at this point, index should be, what is your index? Index is 1. You multiplied index by 3. So maybe you can try running this program and try doing debugging in your editor itself. Then you will be able to see from where the execution is going, from which place to which place. Then you will be better able to understand what is happening. So maybe I can try creating a, so what is happening for, let's say 6, 2 into 3. So index is equal to 0 and d is equal to 1. Then you go to index equal to 1, d is equal to 1. So then index equal to 1, say you will go to index equal to 2, d is equal to 1. So at this point, you would say that 1 is your divisor. Fine. Let's do this now. What are the other cases from 0, 1? So 0, 1, you can do D into equal to P. So you can go 2, index will become 2, 1, 2. So 1, 2, you can decide to choose x equal to 0. So it will index equal to 2. This will become 2. And this is your divisor. Or you can multiply it by 3. So that will be index is 2. And if you multiply it with 3, it will be 6. So the divisor is 6. What can you do from here? Let's do this thing. From 1, 2, you can go index equal to 2. And this is 3. And this is also a divisor. So in the end, you can see 1, 3, 2, and 6 are your divisors. So how will it print? It will go from 1, 0 to, the printing order would be, it will go from 0, 1 to 1, 1, then to 2, 1, and it will print 1. Then it will, so if you see here, from 0, 1, it went to 1, 1, then it went to 2, 1, and from, so it's like from 2, 1, it is showing it went to 1, 3. Okay. Index 1. Index, okay. So this I'm telling after. So this index, at this point, this index has become index plus 1 basically. Because the one that you will be passing in the function would be index plus 1. Okay, I have messed up something. What is this here? It's not compiling. Let's see that. 206. This is not saved or what? Yeah, it was not saved. So now let's see. 1, 1. So initially I started with, instead of doing here, let's do here so that I get an idea key at what indexes I am reaching. So I started with 0, 1. Index is 0, D is 1. Then I went here. I went to 1, 1. Then from 1, 1, I went to 2, 1. Then I came back to 1, 1, and I went to 2, 3. Then I came back to 1, 1. Then I came back to 0, 1. From 0, 1, I went to 1, 2. From 1, 2, I went to 2, 2, and then I went to 2, 6. So essentially, like here in recursion, so you can draw its recursion tree as follows basically. So initially, so the first thing is index. So first thing is index. The second thing is value of D. So initially you have 0, 1. You can multiply it by 2. So at this stage, you can have 2 power x, where x, so you can have 2 power 0 or 2 power 1. So you can multiply 1 by 2 power 0, 1, or you can multiply it by 2. And in this stage, you can multiply whatever number you had into 3 power 0 and 3 power 1. So you can multiply 1 by 3 power 0, which is 1, you get a 1. You can multiply it by 3 power 1, so you can get 2, 3. And in this case, you can see you can multiply 2 by 3 power 0, or you can multiply 2 by 3 power 1, and you can get 2, 6. And at this stage, you stop your recursion and you say that your 1, 3, 2, and 6 are your your divisors. Is this clear? Like, it's very difficult to explain recursion without debugger. If I had debugger, I don't have debugger set up in this. Otherwise, I would have shown in debugger key how it is working. But at least you can get an idea key what is happening at each level. So this is index equal to 0, this is index equal to 1, index equal to 2. And you can see that whatever was number in the previous layer, I'm multiplying it by 2 power 0 or 2 power 1 or 3 power 0 or 3 power 1. So if suppose there was 3 power 2, so the same tree will have one branch more. Anyone else have any doubts in this? Should I go to next topic? So now we will do sieve for this divisors itself. So suppose now someone asks you, given a number n, find divisors of all numbers from 1 to n. One fact that might be useful for you, how many number of divisors a number n has? So what is like order notation for that? Is it order of n, order of square root of n, or something? How many divisors can a number n have? So if you can just remember that it has approximately n power 1 by 3 divisors. So if number n is, let's say, 10 power 9, it can have maybe 10 power 3 divisors. Fine. Now one quick question. How many prime divisors can a number n have? So find out. So for a number n, this time you have to find only the prime divisors. So how many prime divisors can there be for a number n? What will be the order notation for that? Will it be order of n? Will it be order of n square root of n? Will it be order of log n? Or what? Which one of these is true? How many prime divisors can number n have? So how many distinct? So let's say distinct. So if a number, let's say 2 appears maybe like twice. So in 18, you could say, for number 18, you could say 2 into 3 square. 2 into 3 square. How many divisors does this number has? How many prime divisors? How many prime divisors? For 18? 2. How many divisors? How many divisors? Can you get answer? How many divisors? No. 1 plus 1 times 2 plus 1, which is 2 times 3 equal to 6. Is everyone clear? Why is it 6? Because 2 power is 1. So I will do 1 plus 1. Fine. So how many, so you can see like the number of prime divisors are very less. So how many prime divisors for a given n are order of log of n? How many divisors for n? It will be order of n power 1 by 3. So this is a fact. You can just remember it. Very hard to prove. This one is easy to prove. Easy to prove. This fact is like hard to prove. Just remember it. It may be useful at some place. So maybe just remember it. So let's do this part. Why there are only log n divisors? Do you get this part? Why there can't be more than log n divisors? Because you are writing your number as a product of 2, 3, 5, 7, whatever, 11, 13, and dot, dot, dot. So you can see that these 3, 5, 7, 11, 13, all of them are greater than 2. So your number is like 2 into 2. So this number will be greater than 2 into 2 into 2 into 2. Fine. So instead of 3, 5, 7, if you just replace it by 2, in that case itself, 2 power k. So let's say, so this number is equal to n. You replace each, so 2 into 2 into 2 into 2 k times. This is less than equal to n. So 2 power k is less than equal to n. So k is order of log n. Is this part clear? You are multiplying by even larger numbers. If you multiply 2 by itself k times, if you multiply 2 by itself log n times, you will reach to n. But instead of multiplying 2 by 2, you are multiplying by even larger numbers. So you will even quickly reach out to n. So you will take at max log n steps. So this means the number of different prime divisors, they can at max be order of log n. Is this explanation clear to you? Like what is happening? Why the number of, because suppose you multiply 2 by itself log n times, you will reach to n. But in case of like prime divisors, you are multiplying 2 by 3, by 5, by 7. You are multiplying by even larger numbers. So you will reach to n very quickly. So this fact you should remember ki how many divisors are there. So now let's solve another problem. Given a number n, find all divisors of numbers from 1 to n. And this you can solve using prime sieve. So let's call it divisor sieve and let's call it number n. So what do I do? So I start with, let's say, number, let's create a vector of vector int divisors of n, comma. So divisor of I here, divisors of I will contain divisors of number I. Fine. So I'll start from, let's say, d equal to 1, say d less than n, d plus plus. Then whatever are multiples of d, I is equal to d, I less than n, I plus equal to d. Then what I said, divisors of I dot push back d. And so now you are done. At this point you are done. If someone asks you how many divisors a particular number has, you can just, so let's just debug divisors here. And let's run this code for divisors till let's say 13 and see whether it works or not. Okay, it gave segmentation fault. You know why it gave? Because I can be equal to n, so we should make slightly more. So for I equal to 1, say I less than n, work divisors of I. So see, so divisor of 1 is 1, divisor of 2 is 1, 2, 3 is 1, 3, 4, 1, 2, 4, 5, 8, 1, 12 k divisors. You can see there are 6 divisors. So do you understand this code? What is this doing? So I'm iterating over all divisors from 1 to n. And so this d will be divisor of all its multiples. So I'm going over all multiples of d and I'm saying ki d is a divisor of I. So divisor of I, am pushing back d. So this is iterating over all numbers from 1 to n, all divisors d from 1 to n. Then this number d, whose divisor can this number be? This number d can be divisor of only its multiples. So now I iterate over all multiples of D. And whoever is that multiple, you can say that D divides that multiple. So this I, you can say divisor of I, you can push back this number D. So at the end, do you see the correctness of this algorithm? Why at the end it will contain, divisor of I will contain all divisors of number I. Do you get this part? Like, if anyone wants to ask any questions about this part, feel free to ask. Like if you have any confusion or want to ask something, why this is working. So this is like very simple code. You are going over divisors and going over all multiples of that particular divisor and saying for that multiple that I am your divisor. So go over D, find I, says that I is a multiple of D, and you say that this D is a divisor of I. That's all. That's your entire code. So what will be time complexity of this program? Do you know what will be time complexity of this program? It looks like, from a cursory look, it looks like order n square, but it is order n log n, because what do you see? For a number D, you are going how many times? N by D times. So this inner loop runs n by D times. Do you get this part? Because you are going over multiples of D and there can be only n by D multiples. So the inner loop runs n by D. So the overall for D equal to 1, it will be n by 1 plus n by 2 plus n by 3 plus n by 4 dot 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 plus n by n. And now as we see in this expression will be n times harmonic of n. And harmonic of n we proved that was bounded by log n. So this becomes n log n. It might look like n square, but understand that if you are only going over multiples of a particular number, you will be spending only n log n time. You will not be spending n square time. Is this clear to everyone? Is everyone clear why its time complexity is n log n? Great. Okay. So this is called, should I proceed further or should I explain here? If you want, I can proceed further and you can see. So let's go to modular exponentiation.cpp. Okay. So modular arithmetic, do you know basics of that? So it's like, it's really simple. It's not that complicated. So let's do this thing. Let's say you have two numbers, int a is equal to 5. Let's say your mode is, let's say 15. Int a is equal to 5, int b is equal to 10. Then what will be a plus b percent mod? What will be a plus b percent mod? Let's call it t. It will be 0. So modular arithmetic, basically what does it do? uh, it has so when you are say do modular arithmetic modulo a particular number, so your all the numbers should be in the range of, so let's say I have a particular mode to be mode, then modular arithmetic means that do arithmetic in such a way that each number should be in the range 0 to mode -1. So whatever you have, number you have, just keep taking mode of that number. So suppose I ask you this. Uh, so let's say A was 5 times 1,000, and let's say 5 times 15 times 1,000. Now I ask you what will be A plus B percent mod. What will be your answer? Will it be 5? Let's see. No, it's 10. Why is it happening? So what is happening? You can say that A plus B percent mod, this will be A percent mod plus B percent mod. And so you do A percent mod and you apply mod individually. So what is A percent mod? So 15, this number is divisible by 15. So its remainder will be 0. What is B percent mod? Remainder is 10. So 0 plus 10. 10% mod will be 0. So you can like, so suppose instead of that, this number was, let's say 9. So this will be 9. So this will become 9 plus 10, 19. You should do mod again. So 19%, 15 would be 4. So this expression should be A plus B percent mod plus this, you take percent mod again. So similarly, if A was, let's say 10 and this was 12, what will be A minus? So suppose this was 12, this was 10. What will be A minus B percent mod? What should be output? In this case, it should be 2. Suppose this was 10, this was 12. What will be the answer? The answer is -2. But whenever we are doing modulo arithmetic, it's a good idea to keep all the numbers in the positive range, 0 to mod -1. So what can you do? You can add mod here and apply. So if you add mod here, -2 will become 13. -2 will become 13. So the negative numbers, you can just keep adding the modulo in that till you reach a positive number. So that is the mathematics of modulo. So subtraction would be A minus B percent mod would be A percent mod minus B percent mod. And suppose this becomes negative. So in that case, you add mod. Fine. How do I compute A percent B percent mod? Suppose A and B are both positive. What will be A times B percent mod? What will be this? 10 times 12 is 120, or 15 into 8 is 120. So this will be divisible by 15. And this will be some number 12. Because 12 into 11 is 132. And 15 into 132 divided by 15 is 8. And 15 into 8 is 120. So 132 minus 120 is 12. So 12 is your remainder. So suppose this is very large number 199. This number is 199. And if you want to do A times B percent mod, your final number should be in the range from 0 to mod. But if you do directly this, then this number is, so 118%. So let's keep this 10. Your answer should be 0. Because 10 power 9 is divisible by 10. and this is also divisible by 10. So this product should be divisible by 0, but your answer is coming out to be -4. Can you see what is the problem here in this code? Anybody can point out problem in this code? This number a times b is overflowing. That's why it is. So what you can do, you can typecast it to long and do this. So if you typecast it to long, this expression will become in long, and then you are evaluating. You can, long is also written as in 64T in, so you can use the same thing. So now we will go to modular exponentiation. So suppose someone asks you, find out a power b percent mode. So someone asks you, find out 10 power 5%, let's say 123. So how do you find such things quickly? So what is the simplest algorithm? Mod pow, let's say, mode exponentiation, let's call it mod pow. Int a, int b. What is the simplest approach? You say int range equal to 1, and then you go over b and you multiply range is equal to range into long of a percent mode. Let's pass mode as well, and you say return range. Fine. And you say, let's say debug of mod power of, let's say a is 10, b is 13, let's say 2, and let's say 50. Let's do this. What should be answer, by the way, of this? 10 power 2 percent 50. The answer should be 0. So the answer is 0. So let's try by 49. So what is answer of 100% 49? Answer is 2. So is this code clear to everyone? Why this is working? You are iterating b times, keep multiplying by a, and whatever is your answer, you give. Make sure you are using long here because your answer may overflow. So what is time complexity of this basic approach? Order of, what will time complexity of this? Order of p. So suppose p is, let's say 10 power 8, then how much time it will take? B is, let's say 1e8. How much time will it take? It will take a lot of time. Let's see. So it took 1.5 seconds. And suppose this was 10 power 9. And it will take, let's see. It's running. Maybe it might take 10 seconds or something. Yeah, it took 13 seconds. So the same approach, if I have to answer multiple such questions, what is modular exponentiation of these two numbers, it will be difficult for me to do for very large numbers. So how can I do this quickly? So everyone is clear till now? How can I do mod power of a power b in order b time? So let's do better. So there's a very simple identity. So suppose I want to compute a power b. Fine. I want to compute a power. So if b is even odd, let's say b is odd. So I can write it as a power b minus 1 times a. Can I write it in this way? If b is odd, then a power b minus 1. So b minus 1 would be even. So I can write it as a power b minus 1 times a. Otherwise, I can write it as a power. What can I write? a power b by 2 times a power b by 2. Is this part fine? I can write a power b as a power b by 2 times a power b by 2. Because then exponents, when they are multiplied, they will be added. So when you multiply a power x times a power y, your answer would be a power x plus y. So your exponents will be added. This part is clear to everyone. So let's directly write this into a code. Int mod pow of int a b mod. So what do I do? I have to write some base case. So let's say b is equal to 0. So what will be answer if b is equal to 0? Yeah, so b is equal to 0. If a is 0, then your answer will be 0. But here I am assuming that a is greater than 0. Because if a is 0, your answer is 0. Fine. So I am saying return 1. So here assumption is a is greater than 0. Because if otherwise a was 0, my overall answer is 0. Fine. Whatever 0 power you do, the answer is always going to remain 0. Otherwise, what do I do? If b percent 2 is odd, so what do I do? I compute a power b minus 1. So mod power of a power b minus 1, I compute and I multiply it by a into percent mod. So I return this. Otherwise, what do I do? Mod. Otherwise, int range is equal to, I do this and I multiply range by log of range percent. So in this case, b is odd. I can write a power b minus 1 times a. This time I should do a power b by 2. B is even. So I can divide it by 2. This will be an integer. So let's try running this program, the new mod pow. So let's call it mod pow faster. Mod pow faster, mod pow faster. Let's call mod pow faster and see how much time does it take. So the answer in both the cases 46. This one took like really less time. So first of all, do you get like what is happening here? How did I do this mod power faster? What is time complexity and so on and so forth is separate thing. But do you at least get the idea of the algorithm? What is happening? So if b is odd, you write it as a power b minus 1 and multiply it by a. Otherwise, if b is even, you divide it by 2 and whatever is the answer, you multiply it by itself. Fine. So let's go to its time complexity. Anyone wants to? First of all, should I proceed with time complexity? If anyone did not get this, let me know. This is like very crucial idea. If someone has any doubts, feel free to ask. Like, don't hesitate. Is everyone clear what is happening? Why? So you can see if b is odd, you can write it this way. If b is even, you can write it this way. This part should be absolutely clear, and you can see the implementation just follows that idea and does this. Is everyone clear with this? Okay, cool. So what will be its time complexity? Time complexity. So let's see. So you can see that initially you have a comma b. So let's see. And this way. So initially you have some a comma b. Fine. Then if b is odd, then you will make it b minus 1. Then you will divide it by 2. Then you might do subtraction. You might even divide further. But you can see that in at most 2 steps, the value of b will be halved, that it will be divided by 2. So whatever was original b, in at most 2 steps, it will be divided by 2. If b is odd, it will take exactly 2 steps. If b is even, it will take 1 step to be halved. So you have some value of b, and you are in at most 2 steps, you are dividing it by 2. So how many steps can you take? So you have some number b, you are dividing it by 2 in 2 steps. So how many steps can you take in the worst case? In the worst case, you can take 2 times log of b, because in log of, so suppose in single step you are dividing b by 2. How many steps would have taken? If in a single step I keep dividing a number by 2, how many steps will it take till it reaches 1? It will take log of b steps. But here in single step, I'm taking 2 steps to divide it by 2. So in the worst case, it will take 2 times log b. So here you can see that in the worst case, this program will take order of log b. So its time complexity is order of log b. We can omit the constant factors. So this program is much faster than previous programs. The same program you can write without recursing, iterative manner as well. Let me write this. Mod power iterative int a b mod is equal to 1. So while b. So if b is odd, we multiply raised by a. Otherwise, you multiply a by a and you return your range. So let's first run this up and then we'll see. So the answer is more, oh sorry, we did not divide b by 2. The answer is 46. So this program, this iterative program, how this is working. So what I'm doing is, you can understand this program as follows. So suppose your number is a power b. So write b in binary. So suppose your b was, let's say, uh, uh, 3 and a was, let's say, 5. A was 5, b was, let's say, not 3. Let's keep it 6. What is binary representation of 6? We can say 4 plus 2. So its binary representation will be 1 0 1 1 0. Fine. So how can I write? I can write a power 5 power 6 equal to 5 power how much? So this number 110, you can write it as 2 power 2 plus 2 power 1 plus 2 power nothing, 2 power 0 times 2 power 0. So you can write 6 as this thing, 5 power 2 power 2 plus 2 power 1. And you can write it as 5 power 2 power 2 times 5 power 2 power 1. Because this sum of exponent can be written in this way. So what do you do? So essentially what this program is doing, it takes initial value of range equal to 1, and so your B will be 110. Initially B is even, this first bit is even, so it is just multiplying A by A. So in first step, in step 1, 111, the bit is 0, so B percent 2 is even, so this condition won't be applied. So A will be multiplied by itself. So A will become 5 की power 2. Initially A was 1, so what was A? A was 5, so A will become 5 into 5, which is 5 power 2. In step 2, this number has become 1, 1, and this time it is odd. So I will do, my range was 1 here. Now my range will be multiplied by A. So range will become 5 power 2. Fine. And A will be multiplied by 2 again. So 5 power 3. So you can see this number, you are multiplying A 5 power 4, so 2 power 2. And in step 3, it is 1. Range will be multiplied by 5 power 2 multiplied by 5 power 2 power 2, and your A will become 5 power 2 into 2 into the same thing. So it essentially, like, what is happening? So it's slightly bit harder to grasp in one go, but you can see that this number, if it runs like n steps, it will be A power 2 power I. If it runs I steps, this number A will be A power 2 power I. Is this clear? Fine. So it's essentially like what we are trying to do is so this multiplication, like, this is slightly tricky to understand. Maybe let me see some easier way to explain. So okay. So let's try understanding it in this way. So suppose B was only power of 2. Suppose B is power of 2. Then will this condition ever be executed if B percent 2 equal to 1? Yes, it will be executed in the end. Because in, like, suppose B is 2, so initially this in step 1 it won't be executed, and you will have just A is equal to A square, and then in the next step B will become 1, and you will have range equal to A square. So at B equal to 1, this condition will be executed. So essentially, like, what is happening is you are going over the bits from left to right, and whenever a bit is even, So each time you are multiplying a by this thing, a by itself, so that it will be squared. And whenever you encounter a 1, you must add that power. So you multiply raised into that number that is accumulated till now. So you multiply a by that thing. So is this clear? So if your number is, let's say, 110 in this case, what was happening that your final answer should be 5 power 2 power 2 times 5 power 2 power 0 times, you can even say 5 power 0 into 2 power 1, because so you go from left to right. So this type you don't need to do anything, just what, so a will be your 5 power this thing, 2 power this thing. So whenever you encounter in 1, you multiply the corresponding thing with your values. So it's essentially like, I think it will be, it's not that hard to get. If your number is, let's say, 1010, so a power 101, a power, so 1010 in binary. So a power 1010, you could even say like a power 2 power 3 plus, so 1 times 2 power 3, 0 times 2 power 2 plus 1 times 2 power 1 plus 0 times 2 power 0. So if you see from left to right, if you, so this will expression will become a power 2 power 3 times a power 2 power 1. That's all. So you go from left to right, you don't do anything at 0th bit, you just multiply a by itself. But whenever you reach where there is a 1, you multiply your answer by that particular value. So this would be that value. When you go to this one, this will be your particular value to multiply. So essentially, whatever is happening in binary, you are just doing that part. Like you just expand these formulas and try understanding it a bit, you will be able to understand why this program is working. So if your number is, let's say, 10, if your number is just 1, you can see why this program is working. If your number is 10 and 111, try some cases and try understanding why this is working. The essential idea is whenever your bit is odd, you should multiply by whatever a you have calculated till now. You multiply your answer with that a. So when your b is odd, whatever a you have calculated, multiply with your range. Keep going, or like keep going over the bits one by one and keep doing this. So this is modular exponentiation. And I think it is almost 5. If you have any doubt in modular exponentiation, let me know. Does anyone have any doubt? Does anyone has any doubt why this iterative version works in log n? Can anyone explain why this version works in log n? Can you explain our call?
Yeah, hello.
Can you unmute yourself and explain?
Yeah, hello. Is it audible? Hello.
Of like numbers, if you want to know, is 101. You can see that you can write it as 1 times its positional value, 0 times 2 power 1 plus 1 times 2 power 0. So I can even write it as like whatever number is made by 10, you multiply it by 2 and add 1. So what number is made by 10? It is 2. So multiply 2 by 2 and add 1. 1 0 is in binary. Yeah, Prince, feel free to ask.
I have a question, but it's not regarding mod exponentiation.
Okay.
Like, imagine the number is like 10 to the power 10,000 or something, like a very large number.
Yes.
And the mod has to be calculated with 10 to the power 9 plus 7. Like, 10 to the power 9 plus 7 is the standard, like, which we get in all of the questions.
Yes,
And
yes.
I encountered this number like 10 to the power 10,000 today, like in one of the questions. And we had to calculate mod there. And I tried, but I got TLE there.
Okay, so that is like slightly. So if your number is like 10 power 10,000,
Yeah, it was, I think, 10,000 or 1 lakh. I don't remember, but it was a
okay,
really
let's
large
let's say
number.
10 power 1 lakh, and you want to find a power this number percent some modulo. So like there are some interesting properties that you may use. So if you use this algorithm, how many iterations will it take?
Log of B.
Yeah, so what will be log of p? It will be like log of, and in this case b is like 10 power 10,000.
Yeah.
So it will be this, and this number is not that large actually. This number is, log of a power b is b times log of a. That property,
Yes, yes.
So this will become this times log of 10. So this number is approximately around 10 power 6. So if you can write this number 10 power 10,000 in binary, then you can solve this problem. If there were like a single test case, you can just apply the same algorithm and use it.
Yeah.
Do you see like how you can do that? So 10 power 10,000, how can you can say it is same as 2 power 10,000 times 5 power 10,000. So it will be even for 10,000 iterations, and then it will always be odd. Do you see you can write 10 power 10,000 as 2 power 10,000 into 5 power 10,000?
Yes, yes.
So if your number is like fixed number 10 power 10,000, then you can apply this sort of trick. You can write it as 2 power 10,000. So for 10,000 iterations,
No,
the number will be even, then it will be odd.
no, the number was not fixed. Like, it can be anything in that given range.
Yeah, so then your first thing you should do is you convert your number in binary and you apply this algorithm.
Okay, okay. We have to convert it in binary and then try doing it.
Then apply this algorithm, yes. In fact, like usually what happens, there are some interesting properties that you can use. So suppose your number is prime. So suppose this mod is prime. Then there is an interesting property of prime numbers that a power p minus 1 is 1 mod p, where p is prime. So suppose 7 is prime. So whatever number you take, if you do its power 6 modulo 7, your answer will always be 1. This is a property of prime numbers. So let's do that. So maybe, so 1 power 6 mod 7, sorry, 1 power 6 mod 7 is 1 clearly. What is 2 power 6 mod 7? What is 2 power 6? 64 mod 7?
1 only.
1. What is 3 power 6? 1 only. What is 4 power 6? 1 only. 5 power 6 power. So all the numbers a, of course, a should not be 7 or 0, because if a is 7 or 0, this will become 0. If a is 0, a power 6 is 0, isn't it?
Yeah, yeah.
So for a greater than 1, like a greater equal to 1 and a less than p, this property will always be true. This is property of prime numbers. A power p minus 1 is 1 mod p. It's called Fermat's theorem. This property, if you remember that for prime number, you take any number and if you exponentiate it by p minus 1, it will come back to itself. So basically, so this property of prime numbers, if you remember, then the idea is if your number is larger than p minus 1, then you can just, so suppose your number is, suppose I want to compute a power some x mod p, where p is prime. So if x is less than p, then I can just use this modular exponential algorithm and my answer would be calculated in log of p time. Fine. Suppose x is very large. Then what can I observe that if I do x modulo p minus 1, because with each p minus 1 power, the answer is becoming 1. So my final answer would be a power x modulo p minus 1 modulo p. Is this expression clear? Like what is happening here by Fermat's theorem? So suppose you have to calculate a power p modulo p. Fine. So suppose I want to calculate a power p mod p. So I can write a power p mod p as a power p minus 1 times a mod p. Fine.
Yes.
And I know a power p minus 1 mod p is 1 by Fermat's theorem. Whatever be the value of a power p minus 1 mod p will be a. So this will become a mod p. So if your number was 8 power anything x mod p, suppose your number was a power p plus let's say 5 mod p. So what would you do? You can write it as a power p minus 1 plus a into a power 6 mod p. Fine. And you
Yes.
know a power p minus 1 mod p is
That will be 1.
1. So this will be a power 6 mod p. So a power 6 mod p, you can even say a power p plus 5 mod p minus 1 mod p. So whatever number x you are given, if you want to calculate a power x mod p, what do you do first? You divide, you first take remainder of x by p minus 1 and then calculate a power x mod p. That would be same as your original answer. Is that clear?
Not this one. In line 217, you wrote a to the power 6 mod p, and later you converted it to a power p plus
Like,
5.
okay, let's take a concrete example maybe. So suppose a power 17 mod 13. Fine.
Yes.
So this thing would be same as a power 17 modulo 12. A power 17 modulo 12. This thing entirely modulo 13. So what is a power 17 modulo 12? A power 5 modulo 13. Because a power 17 ko I can write as a power 12 times a power 5 percent 13. And you know a power 12, and this expression I can write as a power 12 modulo 13 times a power 5 modulo 13. And this expression I know is 1 by Fermat's theorem to this. So this will become a power 5 modulo 12. Is that clear? Is this person clear? What is happening here?
Yeah, this is clear. I'll try to look into it more. It's Fermat's
Like,
theorem, no?
yeah, so essentially what is happening? So property of prime numbers is as following. You take any number, fine. So you keep multiplying by itself. Whenever you have multiplied it by itself p minus 1 times, which means the number has become a power p minus 1. So then the number becomes 1. So if you multiply it one more times, the number will become itself. So the property of prime numbers is, if you multiply any number by p times, and this number modulo p will become a itself. That is property of prime numbers. So essentially, like, prime numbers are it's called a cyclic group. So the idea of this is, you take any number, if you multiply, and p is your prime. So if you multiply a by itself p times, this number won't change at all modulo p. The value of this number modulo p is going to remain same. This is property of prime numbers. And this is also called Fermat's theorem. So essentially, whatever number a you have, if you multiply it by itself p minus 1 times, which is like a power p minus 1, the number will become equal to 1 mod p. So if you want to compute a power some very large number mod p, what you do, that whatever the exponent be, you first reduce this exponent to be exponent modulo p minus 1. So suppose I want to find a power 2 lakh modulo 13. So you know 13 is a prime.
Yes. So in that case, we don't deal with the number itself. We only deal with the power first and then overall with the number.
So in that case, what you do, you first take the power 2000 and you reduce that power. And what you do, you take 2000 modulo 13 minus 1, which is 12. So 20,000 modulo 12. What is that number? Whatever be that number, you do a power that much, the answer is going to remain the same. So let's try doing that.
And similarly, we can again do, if that number is like larger than 12 or something, we can again apply that formula.
Yeah, but you won't need to apply, because this, if you do modulo, this number has become smaller than 13. So let's do this person. Let's take a equal to 7 and 20,000 comma 13. So what will be its answer? Let's see its answer. And my claim is, this answer should be same as 20,000 mod 12. Fine. These two answers should be same.
Yes.
So let's run this program. So this answer is 3,3. In fact, these two numbers should be same for any number a from 1 to a less than p, a plus plus. So let's p is equal to 13. So I should pass a here, a here. So you can see that 99113, all the numbers are same. So I can do one thing. Let's make it int x, int y, and let me put an assert for this. Assert x equal to y. Like, if x is not y, it will fail itself. So you can see that your assert passes. So this is true for any prime. Int p, let's say it be 31. It will be true for any prime p. So this would be p, this would be p, and this would be
p minus 1.
P minus 1. So whatever prime you take, this is always going to be true. So maybe I'm not sure whether this is a prime, but if it is, this will be true. But it may not be true for a prime. So let's try for a non-prime and see whether it fails for that. It kind of worked for that number. Let's see why it worked for that number. Oh, sorry. It was let's try some smaller prime number. Try for 100, then we will be able to understand. For 100, it doesn't, this thing, 100, it's not true. Because 100 is not a prime. So see, first value is 76, the other is 4. But if this number is 97, this is going to be true. This number, everything is true. All the x comma y are always equal. So this is property of prime numbers. Whenever you do its power p, it becomes equal. Whenever you do its power p minus 1, it becomes equal to 1 modulo p. Fine?
Yes, yes. Thank you, Praveen.
So you can use this property for prime numbers and solve this question.
I used big integer. That's why I think I was getting TLE.
Yeah, so how will you solve that question now? So whatever the large number you have, if the mod is prime, you take that number modulo p minus 1.
Yes, it might have been like that. I didn't know this, so I didn't notice this like pattern there.
Yeah, so try solving your question using this.
Yes, okay.
So one thing like this, so suppose someone asks you int find remainder, and your number is given you is in string, let's say. Because the number is very large, so it cannot fit in int data type.
Yes.
So fine, and you want to find its modulo percent mod. So how do you do that? Does anyone know? Anyone
It
wants
was,
to
yeah, it was something like this only. The question was similar to this, like numbers were in string, so I converted it into big integer.
Yeah, you don't need to convert into big integer. Can you do it easier? So if your number is whatever, let's say 1, 2, 3, 3, 3, 3, so on, very large number, it won't fit in integer or long or anything. And you want to find it modulo. Mod fits in integer. So let's say mod is some prime number. Or this, in this case, it need not to be prime. Any number, let's say 1029. You want to find this.
We
How
can
do you do that?
we can traverse one by one,
Can traverse one by one.
and there is some condition. Otherwise, means if you will traverse from one, then
So so
So
essence.
actually, what we can do is we have to make another string until mod the value of mod is there. No, we have to take that, and whatever it comes under that, we can consider only so much from the position. I mean, from the binary. When I'm saying like from only the first 3 or 4 positions, we have to take something like that.
Okay, let me. So suppose it was not reminder. Suppose that you were given some string and you had to convert into an integer. You want to convert some string to integer. So let's say convert to integer string s. You are guaranteed that this string fits in an integer, and this string is in decimal, no decimal. Fine. Decimal, no decimal. So if your string is 10, your answer should be 10. If your string is, let's say, 159, your answer should be 159. So what do? You initialize a variable, let's say array is equal to 0. You iterate over all strings. So let's say char in s, fine. Then you multiply your answer by 10 each time, because that way you will be making 10 power 2. And let's say you do reg plus equal to ch minus 0, and you return reg. So you do this. So this is very simple. Let's run this program and see what happens. So convert to int of 159. So let's print this. This is not returning or what? So convert to int of, let's say, 159,004. So you can see this answer is same. So what is happening? This is a very simple program. So what is happening? So you are doing essentially, so what is happening? You can write 159 as 100 plus 50 plus 9. So essentially what is happening here, you are going from left to right, and this reg tells you whatever was the previous number. So suppose your number is, let's say 1759, this pretty large. So when you are at this place, except last, so let's take very small number 159. Initially value of reg equal to 0. When you end the iteration, reg will become 0 into 10 is 1 and 1 plus 1 is 1. So at step 1, what is value of reg? 1. Is that clear? Is that clear? At step 1, why value of reg is 1? Because initially it was 0. I multiplied by 10. 0 into 10 is 0. And I added 1 to it. The reg become 1. Is that clear? I'm not able to hear any yes, no.
Yeah,
Yes, Praveen.
I don't,
Hello?
Yes, it's clear.
Did I muted everyone or what? Hello?
Yeah, hello.
Sorry, I mistakenly muted you. Yeah. So at step 1, reg equal to 1. Is that clear?
Yes.
So at step 2, I will multiply reg 1 into 10 is 10 and 10 plus 5 is 15. So at step 3, I will multiply 15 by 10 first and add 9. So 159. So you can see that each time, if I'm considering first x digit, my number will correspond to whatever be the value of those x digits in the decimal notation. So in step 1, only considering first digit, what is my answer? 1. Only considering first 2 digits, what is my answer? 15. Only considering 3 digit, what is my answer? 159. So what is my answer till now? I multiplied by 10 and add the digit. That will be my total answer. Is that clear?
Yes.
So if you want to find remainder, what do? You apply the same code, but now what do? You have to apply mode somewhere. Where can you apply mode? You can apply mode anywhere. It doesn't matter. So you can say range % equal to mode and return your answer.
In this case, like we don't even need to check like if a result is going more than mod or not. We can directly apply the mod.
You cannot apply mode outside this for loop
Yeah,
because
outside
the
we
inner
can't.
one may overflow, but here you may apply directly.
And it will be always the answer between the modulo.
Yes, because suppose this range fits in integer. So one thing you have to take care. So suppose your mode is 10 power 9 plus 7. So in that case, if you multiply that by 10, that will become 10 power 10, and that may not fit in integer. So in that case, you have to take this to long run.
Yes.
So make sure all your intermediate calculations fit into whatever data type you have. If they are not fitting into that data type, then there is a problem for you.
Thank you. Got it.
Yeah, so now solving that question.
Res is equal to 1.
Yeah, sorry, reg is equal to 1. No, reg equal to 0.
For the first digit, it needs to be 0.
Yeah, because I haven't considered first digit till now. When I will consider first digit, so suppose there was a single digit, my answer should be that digit itself. So if I keep it 1, 1 into 10 will become 10 plus 4. So do you get why it is 0? Why not 1?
Yeah, got it.
Whenever you are doing some exponentiation, then it was 1 because 10 power something number power 0 is 1. So here it will be 0. So now you can solve that question of yours, the modulo p minus 1 thingy. So now if someone asks you, int find modulo string, let's say as int mod, and suppose mode is prime. If mode is not prime, you can solve that case as well. But if mode is prime, what do? You find exponent, expo would be find remainder of s comma. What should be the value here?
Mod -1.
Yeah, mod -1, and your answer would be mod pow iterative. Uh, so this was this number power. So this number a power, this was exponents, let's say. So a is, let's say, int. So your answer would be mod pow of a power expo mod. Return. So this would be your entire code. If your mode is prime. So whatever. So suppose your number a, this number, the base is also very large. Then what would you do?
Base is also large, like
Suppose base also fits in string. So let me call it string base, string exponent. Here I was doing exponent, and let's call it, yeah. So then what can I do?
I think we have to do like exponent we have done.
Yeah, you have to do like that. So int new base would become find remainder of base comma. What should be value here?
we mod.
Yeah, this should be mod, not mod -1. Do you get why?
Yes, this one,
Yes.
like we only want the remainder part.
Remainder of that. So suppose exponent was 1. So that number was base itself. So if someone asks you base percent mod, so you should do base percent mod. Fine.
Yes.
So you can do this. If it is not prime, this mod is not prime, then there are some tricks that you have to use. So I will give you a hint. You can, if you want to go into that direction, you can use Euler function and Chinese remainder theorem. Those are like slightly advanced topic, but essentially like they follow exactly the same thing. So whatever you have done till now, they will follow exactly similar pattern. So what were you we doing? So here we were doing mod -1. So here, in case mod is not prime, we will do phi of mod, where phi is this Euler phi function. And then we will do some tricks. So maybe those are slightly advanced topic. I will not, and those are generally not asked in interviews as well. But at least this binary idea, this sort of ideas, they can ask some questions which uses these ideas directly. Even this sort of things could be handy. Knowing like Fermat's theorem is like really easy. So knowing Fermat's theorem could be helpful as well. Anything else?
No. Thank you, Praveen.
Anyone wants to ask anything of this lecture if there's any doubt or some clarification, any feedback or anything wants to talk, let me know.
It was a good session. Like everything we are clarifying things like how all the things are working.
Yeah, I'll share code with you as well. These 4 files I will also share.
Yeah, video will be there in our platform, so we can see also there, because if we will see again it, then we will things all clear again. I think.
Yeah, sure. Like I do like if you write code of these things and debug yourself, you will get like better idea ki how these things are working. And in this case also, like I rather than explaining on text, I thought it's a good idea to write code and see, because it's sometimes people know the idea and don't know how to write the code for that. So that becomes
The recursive part, you said that you can implement it, but you implement it, then only you know that, oh, it's a typical that you have implemented that recursive part.
Yeah. So that recursive part is like very important to understand for interview purposes, because you will find at least one question in most of the interviews where if some question is related to recursion, it will follow this pattern, and it's very important to understand what is happening. So this I according to me, like, everyone should understand why this recursion is working, because this is like so important for both interview purposes and like even in general. So this kind of recursion will be useful in finding some strings with property, finding all permutations, finding all combinations. So you kind of, how do you like, so suppose you want to generate something with some property, how do you generate that recursively is a good idea. So you maintain your state and keep going to the next state till you reach to the end state and you print something. So this sort of idea is very important, and I'll recommend everyone to at least like run this program, maybe run in a debugger, maybe write your own versions of recursion. Maybe try some problems with print all permutations, print all combinations, print all string with some property. So this sort of recursion would be very helpful. When your expression's time complexity is summation of n by I, then it is not n square, it is n log n. And that is the main idea behind many C algorithms. So that is very crucial to understand. Remaining, I think there is not much complex ideas. It was more or less, so GCD was also more or less simple. If someone wants to, one part that I did not prove is this fact. In two steps, the value of max of a comma b will be halved. So this part, if you want, you should try proving. It's not that difficult, it's pretty easy. So try proving this part. If you want to prove, it's good. If you don't want to prove, that is fine. At least try implementing this idea, or at least know this part. Whenever you are starting with the a comma b and you are doing a mod b comma b, the total number of iterations are log of n. They are not like max of ab. They are log of max of ab. So this part is so relevant. It comes handy in multiple interesting places in number theory. But for interview purposes, there might be some question where you are asked GCD. So this might be useful. So one thing that I kind of forgot to tell, how to find GCD of three numbers. I was thinking of covering that.
I think
GCD.
same you have told us here.
Yeah, so this is easy. Like if you want to find GCD of a comma b comma c, this is same as like GCD of a comma b, and take GCD of this with c.
Yes.
So you kind of maintain a variable g, and whatever are your numbers. So let's say your number is all the elements of A is GCD, then you iterate over all A, and what you do is you do G equal to GCD of G comma X. So this will be GCD of all the GCD of the entire array A. So this part is easy. Remaining, I think you don't need much over modular. In modular exponentiation, I think this binary lifting idea is more important. At least if you can implement uh, this part. If b is odd, you subtract -1, otherwise you divide by 2. If you can implement this, you are good to go. This will come handy at multiple places. And handle overflow, that will come handy at multiple places. This part is very important, how to compute remainder of string percent mode. So it's essentially like going from left to right, and at each time you are, whatever is your prefix that you have considered, you have So basically for that prefix, you know the corresponding remainder. So to find the new remainder, what you have to do. Let me know if anyone has any questions related to this or any in general before we end the session. If you have like any feedback, how can we make it more interesting? Was it I feel like it could be a bit monotonous. Was it like a lot monotonous? Let me know.